Yes, absolutely, Tajinda. Ready, as I say, I think we're ready to start. So if you'd just like to welcome people, and we'll hand over to Angelo. Thank you.
So welcome, Good evening to all of you, and thanks for coming for this lecture. So it's my pleasure to welcome my good friend and collaborator, Angelo Bassi, to give the 10th OSMU lecture. Angelo is currently a professor at the University of Trieste, where he leads a highly influential research group on quantum mechanics. Angelo obtained his PhD from the University of Trieste in 2001, working with Giancarlo Ghirardi, who is one of the founders of the Ghirardi-Rimini-Weber-Pearl theory of spontaneous wave function collapse. Subsequently, Angelo was a postdoctoral fellow and a visiting scientist at ICTP Trieste and a Marie Curie fellow at the Ludwig Maximilians University in Munich. In 2006, he joined the physics department at the University of Trieste as a faculty member. Angelo's research passion is in quantum foundations and their relation to gravity, and in particular on testing the limits of validity of the present formulation of quantum theory. No one has done more than Angelo has in promoting research on collapse models, both on the theoretical front and on the experimental front. He has published over 80 research articles on the subject, including in the journals Science, Nature, Physical Review Letters, and Reviews of Modern Physics. His notable works include an underground test of Roger Penrose's proposal on gravity-induced collapse, non-interferometric tests of collapse models using ultra-cold cantilevers, experimental bounds on collapse models from gravitational wave detectors, and testing the gravitational field produced by quantum superposition. Angelo has co-organized more than 20 international conferences, workshops, schools on quantum mechanics and related topics. He was the invited speaker at nearly 50 international conferences and schools. He has been interviewed by the Scientific American and New Scientist with cover stories on testing the quantum superposition principle. He was the principal investigator of the European Horizon 2020 project, TEQ, testing the large-scale limits of quantum mechanics. Angelo was also the chair of the Cost Action Fundamental Problems in Quantum Physics, and currently is chair of the Cost Action Quantum Technologies in Space. In 2020, the New York Times carried a feature article on Angelo titled "The Rebel Physicist on the Hunt for a Better Story Than Quantum Mechanics." Today, we'll hear from Angelo himself about that better story. Please go on. Over to you, Angelo.
Thank you. Thank you very much, TP, for the presentation. Thank you for the invitation to give this lecture. And thank you for all those that are here connected today. So it's about, as anticipated by TP, basically it's about models of spontaneous wave function collapse. So the idea that quantum theory, with quantum theory, we mean the Schrödinger, the dynamics of quantum theory. So at a non-relativistic level, the Schrödinger equation is not entirely correct. It's a good approximation of a deeper level theory. And collapse models perhaps not aim to be that deeper level theory, but to give an indication towards that theory. And for those of you that attended the lecture of Steve Adler a couple of weeks ago, you will see some connections to that talk, because also we worked together and he worked on the same topics for quite some time. Okay, so just we'll say a standard introduction about the problem with quantum physics, which is always good to review a little bit. So the theory is a theory that works perfectly so far. So the issue is not that quantum theory is failing somewhere from the point of view of experimental evidence, but as it is failing as a fundamental theory of nature because it's not entirely well defined. The theory assumes in its standard formulation a division of the world between a classical world and a quantum world. A quantum world, the microscopic world, which is governed by a wave function, then physics is entirely encoded into the wave function, be it the wave function of the Schrödinger equation or the wave function of the Dirac field or whatever. But then there is a classical world of observers and apparatus that make measurements on the wave function. And then there is the rule that after the measurement, the wave function collapses, that the outcomes are random, distributed with the Born rule, and there is all this phenomenology of measurements. But if you take it seriously, there is this division between a classical and a quantum world. And it is, if you go back to the original papers of Bohr and debate with Einstein whatsoever, this division was clearly spelled out. Now it's been a little bit forgotten over the years. And then you have a problem. I like this quote of Steven Weinberg. You can quote Bell and many others, Einstein himself, Feynman also. So the Copenhagen interpretation assumes this mysterious division, which should not be part of fundamental theory. First of all, because the fundamental theory should be a unified theory when there is no real division. And second of all, even if there is a division, it should be clearly spelled out. The fundamental theory should precisely tell what there is and how it behaves. Quantum theory fails to do so. It fails, again, not from the practical point of view. Everything works perfectly, but from the fundamental point of view. And here, the rule of the game, here, the point is to go to the foundations of our understanding of nature and to understand whether our theory gives a coherent description of nature. And quantum mechanics does not do so in its present and standard formulation. Okay, so the general, here I jump to collapse models, but the general attitude, I think that everybody would take it, or at least, I mean, you can contradict me, or by the way, you can stop me, ask questions anytime. So the general idea is that if the world is quantum, in whatever sense it might be, it should be the entire world should be quantum. There should be a wave function for every physical system, or a wave function of the universe out of which somehow you get the wave function of a subsystem. So there is no division, just a unique quantum world. And then the question comes, but how do we find, we as a classical objects, do we find a place in this quantum world? Given that the wave function spread according to any equations, a quantum equation, the wave function spreads, and worse than that, in some sense, it becomes entangled. Everything becomes entangled with everything else. There is this abstract state vector in an abstract Hilbert space, and where do we find ourselves in this description as classical objects moving classically? This is the issue with quantum mechanics. If you remove the boundary, then the quantum world floats into the macroscopic domain, and then it's not trivial, it's not obvious how to recover classicality out of that. There are proposals for that, hidden variable theories, Bohmian mechanics is a solution, the many world theory is another proposal. Here we'll talk about another such proposal, which goes again under the name of models of spontaneous wave function collapse in a shorter way, collapse models. And the fundamental idea is that there is the wave function, there is a wave function of the universe, but the wave function of the universe does not obey the Schrödinger equation, or again, in a relativistic setting, the Dirac equation, whatever. With Schrödinger, I will limit myself to the Schrödinger equation, but with Schrödinger, basically, I mean a linear unitary evolution. That is the main issue. It's not so much that it's not relativistic and given by Schrödinger. So the idea here is that the unitarity is broken. The dynamics is approximately unitary in certain circumstances, but in other circumstances, this unitarity is plainly violated. For example, in measurement process, for example, in the macroscopic world. And then, if this is the program, the goal is how to achieve it mathematically, how to write down such an equation. And that's basically all one should say about collapse models. Collapse models are a consistent way of implementing this idea that the unitary evolution of quantum mechanics is not exact, but approximate. And one might think, okay, well, why do you want to give up a unitarity which has some very, very nice features? Well, again, the answer is because of the measurement problem. But also, if you think of the history of physics, linearity is typically a very special property. It's only approximate. So Newtonian potential is linear because it's the weak field limit of a general relativity. And also in many other physical situations, air, water, whatever, you have linearity and you have a wave equation because you have a small displacement. You have weak effects. But as long as the effect becomes stronger, nonlinearity enters into the game. So it's also, in a way, from the physical point of view, very natural to consider the linear behavior a weak field limit of a nonlinear behavior. And then you can consider collapse models as such as a possible next order expansion towards nonlinearity. Again, as these are phenomenological models, not a fundamental theory. They just suggest a way, a direction of research, a way to go. So the dynamics is modified in order to introduce nonlinear and stochastic terms. And there you have just a non-comprehensive list of the people that work in the field. Ghirardi, Rimini, Weber, Pearl, Dioshin, Gizen were among the first to consider the mathematics of these models and their mathematics. Then Adler, as I said, Bedingham, Tumulta, myself, many other people. I mean, I didn't even try to make an exhaustive list. Okay, so Just to show you an equation at least once, then I will be very much descriptive in the rest of my talk. This is a typical equation of a collapse model in the continuous version. You can have discrete collapses, but it would be kind of more natural to think that there is a continuous process in space. So this is the equation where the first term is the usual standard quantum dynamics. So psi is the wave function of any system. Take the universe if you wish. H is the Hamiltonian, whatever Hamiltonian that is of the standard model, ambitious. Of the system, and then the rest is the collapse of the wave function. You see that the terms are a little bit awkward. So here there is a lesson to learn. So these terms look awkward. The Hamiltonian terms are much nicer, but actually there are specific reasons why the collapse term have to have this form and not another form. This would bring us a little bit far away because I have to explain that typical nonlinear modifications of the quantum dynamics lead to superluminal signaling, instantaneous signaling, which is not related to a non-relativistic limit. Even in relativistic setting, if you introduce nonlinearities, you would have you would open to the possibility of instantaneous signaling. If you want to avoid instantaneous signaling, then you have to buy the mathematical structure of collapse models, which is the one that is shown here. What are the main ingredients? First of all, it's a nonlinear, again, contribution to the evolution because the wave function enters more than once into the equation, and that induces the collapse of the wave function. So the superposition becomes narrower and narrower over time. So there is two competing effects. There is the Schrödinger term that spreads the wave function in space, and then there is the collapse of the function that shrinks the wave function. And then case by case, one has to check who wins of the two. Eventually, you find an asymptotic stable solution. It collapses the wave function because the dynamics is nonlinear. It collapses the wave function in space because the operator that injects the nonlinearity is a mass density operator. A DAG is the creation operator, A is the annihilation operator. In the simplest version, you can take spin if you wish. It's not important. It's just that you have a density operator, and then if you put a mass in front of it, you have a mass density operator. So the reason why you have a density is that precisely because you want to localize objects in space. Density means space in this second quantized language. And then for a matter of principle, but also for compatibility with the experimental evidence, you would take a mass proportionality. So a heavier particle collapses faster than a lighter particle. That makes pretty much sense. That's the reason why you have a mass density. The collapse is random, it's not deterministic because you have a noise. W of t is a white noise, is a stochastic process, which is white in time, so it's a linear process to be precise, and it's correlated over space, and there capital G is the correlation function, and we'll come to that. So the collapse is random, and actually you recover the Born rule. So by requiring that the collapse of the nonlinearity is such that you want to avoid superluminal signaling, as a byproduct, you recover the Born rule. So it's a nice way to say it. The Born rule is not assumed. So you can derive it by considering a microsystem interacting with a macro object in a measurement-like situation. You solve the equation, and you will see that the outcome of the measurement is distributed with psi squared, where psi is the wave function of the microsystem. This is one nice thing. And then there is an amplification mechanism, which is important. The strength of the collapse increases with the size of the system. So you choose the form of the equation once for all. You choose the parameters. I will come to that because that will be most of my talk, how to constrain the parameter from experiments. You choose the parameters once for all. And then you apply the equations for two different situations. And you will see that if the system is a small system, then the collapse is negligible with the smart choice of the parameters. But if the system is a large one, the collapse is very fast. So this is the essence of collapse models. So if you want to summarize the content of that equation in a few pictures, here is the content. So if you have just a microscopic system, so the important point is a superposition in space. First message. These equations collapse superposition in space. I will come to other degrees of freedom. So space for now. If you have a microscopic superposition, basically nothing happens. It's a quantum system. It behaves quantum mechanically, modulo tiny deviations. And this tiny is important if you want to have experimental evidence. But the growth of the dynamics is the quantum dynamics. But if you have the Schrödinger cat, if you have a macroscopic superposition, cat here plus cat there, whatever here plus there, with many atoms, many particles inside, then there is this amplification mechanism. The collapse gets amplified with the size of the system to the point that the Schrödinger cat cannot be in a superposition. The dynamics forbids that. The superposition of a cat is a highly unstable state and dies immediately. Or to be more precise, you're not even able to create the superposition because the equation kills it before you're even able to create it. So the cat or whatever, table, chairs, me, you, are always well localized in space. So well in space that we behave for all practical purposes like points moving according to Newton's laws. So in collapse models, there is the wave function, so it's a wave theory, but it's a nonlinear wave theory. And for specific systems, you have a point-like classical behavior as an effective approximation, as an effective description. But of course, not all many-body systems behave classically, because we know experimentally that some many-body systems are quantum, like cold atoms, like supercurrents, BCs, superfluidity, these kind of things. Well, all these experiments are macroscopic or mesoscopic, if you wish, quantum systems in the sense that there is a large number of degrees of freedom. But in none of these cases, there is the superposition system here plus system there. It's not superfluid here, but superfluid there. Supercurrent here, supercurrent there. Supercurrents are always located. They just run in opposite direction, for example. With cold atoms, it's not cloud here plus cloud there, but it's every single atom here and there. So it's not a macroscopic superposition from the point of view of collapse models. There are many atoms, but each of them independently in a superposition. It's not a huge entangled state. And then the collapse, again, is not effective. Collapse models, otherwise they've been falsified experimentally. Collapse models tolerate such quantum superpositions very well. Again, modulo tiny deviations. And these, again, are important for experiments. And then what happens to the other? So first here, so you see that in this way, I think this is basically the most important lesson of collapse models, at least from my point of view, that you can consistently modify the Schrödinger equation, such a the fundamental structure of the Schrödinger equation, which is the linear unitary evolution, without making any big trouble. The result in dynamics is still a physically plausible dynamics, which is compatible with experimental evidence. So this is I think it's an important message. What happens to the other degrees of freedom, spin, momentum, whatever? So in general, these other degrees of freedom are not affected by the collapse unless the superposition in these degrees of freedom turns into superposition in position. The typical example is momentum. If you have a particle which is localized in space, but in a superposition of two different momenta, but otherwise localized, the wave function will not be affected by the collapse. But after some time, the superposition in momentum turns into a superposition of position. You have two different velocities. So the wave packet separates in two parts. And then now you have a superposition in position, which is killed by the collapse. So the moral is that the collapse only in position, but effectively it collapses also in momentum, of course, without violating the Heisenberg associativity principle. All relevant physical quantities are very sharply localized as much as possible. Okay, so these are collapse models. So from the theoretical point of view, there is a lot to say, which I will not say today. So the issue, the compatibility with relativity. So these models are non-local because you have to recover quantum non-locality in Bell's experiments. When you collapse here, you collapse also there if an entangled particle. If you don't do that, then you are not capable of reproducing Bell's experiments. And then if the collapse is non-local, then there is an issue with relativity. It's an open problem. Then, more ambitiously for me, is what is the origin of the collapse? So where do these models come from? I don't consider them as fundamental, so they come from somewhere. So Adler has an idea coming from trace dynamics, also TP has a similar idea. So this is another fascinating subject, which Roger Penrose, I will tell later, has another idea. I will not talk too much about this because it's an open field of research. I wouldn't have much to say. So TP has more to say about it. So this is one line of research. The other line of research, the one I followed, is to make a comparison with experimental evidence. You modify the Schrödinger equation, So you modify the dynamics, and so you should see different predictions. Of course, tiny deviations, otherwise we would have seen these collapse models already. So this deviation must be tiny, and you have to carefully check whether they are there or not. So how do you test collapse models? So there is a direct and indirect way. Since we are talking about nonlinearity, we are talking about breaking the superposition principle, the obvious way is to do interferometry. You take a system which is as massive as possible, you create a superposition as large as possible, you leave it there in the refrigerator for as long as possible. After some time, you open the refrigerator and you see, is it still there or not? So you do some interferometric test. Is it still there or not? If it is still there, then collapse models are wrong. If it is not there, in spite of the fact that you carefully control the system, and so the level of noises was low enough, if the superposition is not there, then you have to ask yourself, why is it not there? Is it because the superposition principle is violated, or perhaps just the experiment was not good enough? So that would be the beginning of a detailed research. So there are pros and cons in this in this program. The pros is that this is a direct test of the superposition principle, which is something important. I sponsor test and superposition principle is more important than collapse models, of course, because we are testing the fundamental property of one of the fundamental theories. So it's like testing the equivalence principle of general relativity. And for me, in some sense, it's kind of a mystery why so much effort has been put in testing the equivalence principle and not so much in testing superposition principle. It's on the same level, because if at some point you find a time deviation from the equivalence principle, then general relativity falls apart. General relativity is deeply rooted in the equivalence principle. If the equivalence principle is wrong, even by a time deviation, then everything falls apart. It's the same with the quantum mechanics. If the superposition principle is wrong, then quantum theory is wrong as a fundamental description of nature. It's not that you just fix a screw a little bit and then you go on. No. You have to find a new theory. So it's fundamental to test the superposition principle. And collapse models enter into this game by giving an alternative, a rival theory, so that you know where to, they give an indication where to look for possible violations of the superposition principle. The difficulty, the cons is that it's very difficult to do such experiments. It's very difficult to isolate a large enough system because there are always noises. It's difficult, but also it's difficult because it's intrinsically difficult, but it's difficult also because the community didn't put so much money and effort into that. And so I sponsor this kind of experimental research. And there are groups doing, the group of Hendrik Ulbricht. Now, TP, you mentioned that he will talk later this month, so he's doing also this. So I think it's cornerstone of experimental physics to test the superposition principle. Again, way more important than collapse models, but it's also a test of collapse models. But there is also a non-interferometric way of doing tests of collapse models. The point, and I want to spend some time on this now. The point is that when you so there is a noise, the collapse is triggered, mathematically speaking, is triggered by the noise. The noise collapses the wave function, but it's a noise. Like any noise, it shakes the system. So the system doesn't go along a straight line. If you wish, the average position, if you want to be more precise, doesn't go on a straight line for a free particle. The particle jiggles, even if the wave function is localized, is in a kind of a classical state. It doesn't jiggle only when the wave function is delocalized. The system jiggles everywhere, every time, always, because the noise is always there. And so this opens to the following strategy. Forget about superpositions. Leave the system in a classical state and just accurately monitor its position. Is the motion the one described by classical mechanics, given the noises, or quantum mechanics with the addition of zero-point fluctuations? Or is there an extra jiggling, an extra noise? That is the non-interferometric test. What is the advantage? These kind of experiments are orders of magnitude easier to do. Again, you don't have to create a superposition. You just have to look for the motion. But of course, it's a tiny effect. So the experiment is not trivial. The backside of the story is that it's not a direct test of the superposition principle. It's an indirect test. And here I like to make this analogy with gravitational waves. When was it? They saw this loss of loss of energy in the spiral of two binary stars, I suppose, and the people won the guys that saw it won the Nobel Prize. This was the first indirect evidence of gravitational waves. No energy was lost in gravitational waves, and the two and the binary system was collapsing one on top of each other. It was one of the most remarkable agreements between theory and experiment. They won the Nobel Prize. They didn't see gravitational waves, but they won not TP. They did win the Nobel Prize, right? Do I remember correctly?
Yeah.
Yes, I think so.
Hulsen-Tanner binary pulsar.
Yes.
Did win the Nobel Prize, yes.
They did. So it was a remarkable result, even if they didn't see gravitational waves directly. We had to wait for LIGO. That's the same story. It would be here. It would be, so if you see this extra noise, it's not a direct test of superposition principle, but it's the test that there is something more than quantum physics, and that opens to a completely new research. So I want to make a point here. So what about this noise or this jiggling associated with the collapse? Because when we worked on the Dioschi-Penrose model, and basically we disproved the model experimentally. The experiment was this kind of indirect test. I will tell about that later. So we indirectly tested the model and we indirectly disproved them. And Roger Penrose claimed that, okay, nothing to complain about that, but this is not the idea that I have in mind. The noise is not part of my story. In my way of considering the collapse, there is no extra jiggling, there is no noise. So your experiment is fine, it's good, but doesn't refer to the way I would implement the model. So we took that on board, and actually the reference is there in the middle, the right part of the slide. We took that on board because, I mean, I was convinced that it not be done. And so we proved that in the very general, that is a PRL that appeared recently, in very general terms, that if you have a whatever dynamics that collapses the wave function in space, so it does collapse, and it's translational invariant, then you have jiggling. So the jiggling is not just our way of doing the collapse. Of course, and if you want to avoid superluminal signaling, there is always this thing in the back. You want to have a consistent model that doesn't allow you for superluminal signaling. So it's not just our way of doing that. It is in the current framework of quantum theory. So in another framework, another theory, I don't know. But in the current framework of quantum theory, if you want to inject nonlinearities in the form of the collapse without doing superluminal signaling, and you just buy translational invariance, then you have this jiggling. So it's a fundamental property. So in that sense, it's a fundamental property of any modification. So it's more fundamental than one would think. Okay, so how to test to test collapse models in the indirect way. So basically, the idea is very simple: take the system and monitor its motion, and then you have to choose the correct platform. Of course, there are many platforms. Those that we worked on was cold atoms, because the people, experimentalists, are very good, have a very good control of cold and ultra cold atoms by now. Cantilevers, so it will be the talk of Hendrik Ulbricht in a couple of weeks. Again, have very good control of the motion of the optomechanical systems, or emission of radiation. Why emission of radiation? Because if you have a charged particle that jiggles, it is accelerated, it emits radiation. And then electromagnetism, you have an excellent control of electromagnetic property. So these are very natural systems to look at. Okay, so tests of the Dioschi-Penrose model. So Dioschi-Penrose model, the equation is the one that I showed you before. The difference is that, what specifies the model is the choice of the correlation function, which is given there. G is basically the Newtonian potential, 1 over r, and then you have capital G because it's related to gravity, and of course h bar because we are talking about quantum systems. So that this is the Dioschi-Penrose model, and I will tell you a bit more about that. Of course, if you have a 1 over x function inside integrals, then you have divergences. The integrals do not converge. So you need to introduce a cutoff. So you have an effective cutoff, which could be, you can consider that as a high energy cutoff in momentum, because this is a non-relativistic model, or equivalently, you can give an effective radius R naught to otherwise point-like particles. I will speak in terms of a radius, of an effective size to macroscopic particles, but you just can turn it into cutoff in momentum. So there is an effective size that you have to put in the model. Again, this model is a simple model, it's non-relativistic. You cannot ask too much from this model. And everybody, so Dioschi and Penrose, of course, were very well aware of that, and they also speak about a cutoff or whatever the name they gave. But how do you choose the size of the cutoff? Here, there are differences between Penrose and Dioschi. So Penrose says that the cutoff depends on the type of system that you consider. And I mean, if you know a bit about the story, I will tell you, otherwise it's another talk. Basically, the cutoff is equivalent to the effective size of the wave function of the system computed by using the Schrödinger equation instead of the Schrödinger equation. I don't want to tell more about that, just take it as a recipe. There is a specific equation, the Schrödinger equation, that you apply to the system that gives you an effective cutoff and an effective size of the wave function, and that's the effective size of the system. I know. The OSI instead originally fixed it as the Compton wavelength, which is a natural way to speak about a non-relativistic versus relativistic regime. This was the original idea, which was later abandoned, and it favored like a free parameter to be decided by experiment. So a little bit of Penrose. So the difference between Penrose and the OSI, often they put it together, and there is a reason for that, but actually they have a difference. There is a difference. They work independently most of the time. So what does the Penrose say, roughly? So again, probably TP knows the story better than me, but I'll try to reproduce it. So Penrose says that when you have a superposition of matter, so first of all, Penrose acknowledges the measurement problem. There's a problem in quantum theory. So what is the way to fix it? The way to fix it for him is gravity. So gravity comes before collapse models. Collapse models would be the output of the research, not the input of the. So Penrose says the following. So if you have a superposition in position of two matter systems, the cat here and there, then in some decent form of quantum gravity, you would have a superposition of different spacetimes, a superposition of spacetime with a bump here, and a superposition of spacetime with the bump there. And then he gives an argument as to why in the proper quantization of gravity, the dynamics would be such that this kind of superposition is unstable. And mainly, I mean, so this is a bit technical, and also I know a little bit about that, because with this kind of superposition, the time evolution operator is not well defined, and not well defined means an instability. So for him, the proper quantum theory of gravity should not be linear and unitary; it should be non-linear. And then there are these instabilities, and that's the end of the story, because he didn't build a theory, because it's a very gigantic job to build such a theory. But he tried to do some phenomenology and tried to estimate the decay time of such a superposition. And then you see the picture from him, basically uses the Heisenberg-Uncertainty principle between time and energy. The lifetime of such a superposition is h bar over Eg, where Eg is the gravitational content, so to say, of the superposition in Newtonian terms, if you are at a non-relativistic level. And then you can easily understand that a superposition of the Schrödinger cat has a gravitational content which is way larger than a superposition of an atom. So a superposition of an atom has a long lifetime, a superposition of a cat has a short lifetime. But if you plug the numbers, you can read in the book by Penrose, the shadow of the minds, I think. And then if you plug the numbers, there is a kind of interesting magic. So here there is no free parameter, because the mass is the mass, the cat of an atom, capital G is capital G. Whatever there is, the numbers turn out right. An atom lives long enough to be compatible with the experimental evidence. A cat, a superposition of an atom. A superposition of a cat doesn't live long enough. It almost immediately collapses. And so this is an indication that gravity is strong enough to guarantee the quantum to classical transition, but weak enough not to be ruled out by experimental evidence, of course, in playing a role in collapsing the wave function. Okay, so this is the idea of Penrose. What is the input of the OSI? The OSI was able to write down the dynamical equation, the one that you see here, basically, that implements Penrose's idea. That's why it's called the OSI-Penrose model. The Penrose stops in giving the phenomenological time lifetime of a superposition. The OSI gives a dynamical equation that reproduces that lifetime. Okay, so we did test the experiment with the radiation emission. So not we, of course, I'm a theoretician, I am. So we did the theory, a group of Catalina Curseano in Gran Sasso. So the theory, first of all, so the system jiggles. So if you have particles, charged particles, they emit radiation. So if you take an atom, every proton, every electron emits radiation. The calculation is awful, but with some approximation, you can get a nice formula, which is the one there. This is the number of photons emitted. So it's a rate, number of photons per unit time, per unit frequency. And then you see that apart from numerical factors, you have all the constants, capital G because it's gravity, E because we are talking about light, C because we are talking about light, R not the cutoff of the model, omega, the frequency, and then capital N and capital NA, which is the size of the system. More atoms, more particles you have, the more particles you have, the more photons should come out. It's a very tiny behavior. So you see that so omega k is the frequency of the photon, so it is k. So you see that the emission rate goes like 1 over k. You can have an intuition that the spectrum, the spectrum of the emitted radiation is horrible. So we are just analyzing the tail, the high energy tail of the spectrum, which is easily to compute theoretically. And there you have the energy range where this limit is valid. So this is the theory. I will not go much into the experiment because I'm not the experimentalist, but it was a germanium detector, an ultra pure germanium detector, and the experiment was carried out down in the Ground Sasson laboratories. This you see inside. So in the almost the cleanest possible environment in the world, or among the cleanest possible environments in the world. But so this is the data taking, the histogram there of data taking, the black one. Again, this has been cut off. It continues on the left. This is just the part that we were interested in. So the black one is the data taking, about 500 counts over 2 months. So you see very few counts. How much of them there are per day? You count them, really, it's counts. You count them very rarely, because these are rare events. So you need a special technology to understand that. But then you know that there is a background noise, and experimentalists have worked for a long time to simulate the detector and to simulate the expected signal, to simulate the noise. And that's the green one. And you see that the green one superimposes quite well with the black one. So the green one means that this is a signal that it is expected, that we know that comes from known physics, some radioactivity in the germanium detector, and a cosmic ray that went through the mountain and anyhow hit the detector, this kind of thing. So this comes from known physics. So this has to be subtracted. So morally, at least, of course, you have to do a proper statistical analysis. I'm talking as a naive theoretician. Out of the 576 counts, 506 should be eliminated because they come from known physics. We know where they come from, statistically speaking. So there are only 70, so very few counts. Almost nothing happened in this detector. By the way, these are the detectors that are used for dark matter searches, of course. And so, if you have so few counts, that means that the radiation emitted according to the Yoshi-Penrose model cannot be strong. Otherwise, you would have seen it. The model has the parameters have to be the model has to make a very weak prediction, and that's where the strong bound comes. You see it there. So you have R0, you have in a logarithmic scale. The colored bar are exclusion regions. So the value within the colored region is excluded. You see that in the theoretical formula, R0 is in the denominator. So if the smaller R0, the stronger the effect. So that's why you have a lower bound, because the model gives a stronger prediction for lower values of R0, because lower values of R0 means a higher energy cutoff, so you have stronger effects if you keep high energy effects. So the blue and the red one came from the literature already there from neutron stars and gravitational wave detectors. The green one is from this experiment, and you see that the green one, first of all, is between 2 and 3 orders of magnitude stronger than the other one. But most of all, it excludes the red circle there, which is the theoretical value for the prediction of R0 according to the recipe proposed by Penrose. So in that sense, the moral is that we exclude the Yoshi-Penrose model in the simplest formulation. So in this specific sense. So if you take the equation there, if you accept the recipe of Penrose to compute the parameter R0, then that's excluded by experiment. Does it mean that the idea is ruled out of? No, because these are phonological models. So it could be that the simplest model is wrong. You need a more complicated model. For example, the noise is white. White noises don't exist in nature. There's always some color. So this is the beginning of a research, but the model in the basic formulation is not compatible with experimental evidence. And that was one of the first times where a collapse model was actually excluded. I would have preferred to confirm it, I have to say, but this is also a result. Okay, so just Just to give you an idea, so we are working together again with the experimental group of Catalina in Gran Sasso in extending the analysis. So the 1 over k behavior of the emission rate is just the first order perturbation theory calculation. Then you can go to you can make a more refined calculation, and then you can see that you have some modulation. So instead of having the blue line, the 1 over k behavior, the tail, if you go to higher orders, you have some modulation, the red curve. And then, for example, so it becomes interesting because everything has a 1 over k behavior. So you don't see a signal there. If you want to see a signal, you want to see some peaks. So there you have the peaks if you go to a high order analysis. So you have some peaks, so you have a structure. And so you have a better way, a better theoretical prediction to compare with experimental evidence. And also you see a difference between the CSL model and the DP model. The two models predict a different behavior. To first order, it's both of them 1 over k. But if you go to higher order, then the story becomes more complicated. So it's an interesting story, actually. Because it's interesting because it's light-matter interaction, which is historical, is one of the most fascinating problems in theoretical and experimental physics. So what about the CSL model, the other model? Again, the equation is the same, but basically the correlation function is different. It's not just 1 over a, now it's a Gaussian. Because the idea that when you think about a correlation function, what do you take? You take an exponential or a Gaussian. Ghirardi, Rimini, and Weber chose a Gaussian. So you have a width of the Gaussian, RC, which is the resolution of the collapse, and you have a coupling constant in front, lambda, which is the strength of the collapse. So now you have two parameters. So the model is a little bit more complicated. And this has been studied a little bit more from the experimental point of view. So here there are some comparison with the interferometric tests. So here you see the parameter space of collapse models, so RC on the horizontal axis, lambda in the vertical axis. So it's a two-dimensional parameter space. The one of the Yoshi panels was a one-dimensional, was just one line. Now you have a plane. You have a plane. So the black dots are theoretical suggestions about the possible value of RC and lambda by Ghirardi, Rimini, Weber, and by Adler. What is the moral? If you accept the value of Ghirardi, Rimini, and Weber, you are saying that the collapse is ineffective in the microscopic world, in the mesoscopic world, and becomes effective only when you go to the macroscopic world. So atoms, viruses, molecules are fully quantum, only the cat, the Schrödinger cat is classical. Adler instead, for reasons that you can read in the literature, related to latent image information, he considers that the collapse should occur earlier in the mesoscopic domain. So lambda, you see, is shifted by about 8 orders of magnitude. It's 8 orders of magnitude stronger. The value of RC is more or less 10 to the minus 7 meters. Why 10 to the minus 7? Because RC dictates the division between a macroscopic distance and a microscopic distance. So 1 meter is macroscopic. 1 angstrom is microscopic. 10 to the 7 is a number in the middle. It's a mesoscopic distance. It could have been 10 to the minus 6, 10 to the minus 8. It's 10 to the minus 7. So it's a mesoscopic distance. Okay, so these interferometric experiments are all really starting from the top left. So these are single atom interferometry, single atom. So the mass is small, 1 atom, 87 in this case atomic mass units. But the superposition, that's why the paper went on Nature, was the largest matter superposition ever detected, about half a meter. So it's like this, half a meter, a little bit less, but about this. So matter, at least a single atom, can live in such a huge superposition in space. And the superposition time is 1 second. So there's also a macroscopic time. So everything is macroscopic except for the mass. Then on the bottom left, this is the group of, in the top left was the group of Mark Kasevich in Stanford. Bottom left, the group of Marcus Arndt in Vienna. They have everything mesoscopic. So the mass is much, much bigger. It's 10 to the 5 atomic mass units. So it's 4 orders of magnitude more. They gain in mass, they lose in delocalization distance. So now it's 10 to the 7, minus 7 meters. It's not almost 1 meter. And also in the lifetime of the superposition, milliseconds instead of seconds. Then on the right is the group of, wow, now the name in Oxford, Ian Walmsley, in Oxford with diamonds. So the internal phononic superposition. Phonons is a collective motion, many atoms. but it's a small displacement, and the lifetime is very short. So you see that experimentally you have to choose. Do you want a big mass? Then you, at the moment, you lose in delocalization distance and in lifetime. You want to have a smaller mass, you can have a larger delocalization distance. But it's not possible at the moment to maximize all three parameters. And the bottom line is that the excluded region is the colored region on the top. You see that this exclusion region doesn't test the idea of Girardi, doesn't test the idea of Adler. So they're not, at the moment, these experiments are not good experiments for collapse models, for the CSL model. It's not the experimentalist's fault, of course, there's challenging experiments. But this tells a very important story. This tells you that the superposition principle has been very well tested at the microscopic level and at the very early mesoscopic level. But it's not been tested in the full mesoscopic level, at the full mesoscopic level, and not even, and even less at the macroscopic level. We are very much ignorant about the validity of the superposition principle in nature. Research focused on specific systems. And that's, again, an important open question. You will see now that in non-interferometrically, you can do much better. With cold atoms, so I want to go towards the end so we can leave time for discussion. With cold atoms, you control the motion. They don't jiggle too much. So the top left corner of the parameter space has been excluded. Or again, this radiation emission applied to CSL, the yellow region has been excluded. Gravitational wave detectors, they are fully classical. Who cares if they're classical? You want to see the jiggling, and gravitational wave detectors have been made in order not to jiggle too much, otherwise you don't see gravitational waves. So they are perfect candidates for testing collapse models. And you see that they kill the entire region on the right. Then cantilever experiments, which are dedicated for collapse models, so they target the middle region, and then you improve. No, this is not being confirmed, this thing, so the end is here. And this is the current status in testing collapse models. So you can say, well, I mean, you kill these models. No, we didn't kill these models because most of the region, no one thought that, I mean, it was clear that most of that colored region would have gone anyhow. Because you see, Adler and Girardi aimed at a specific region there. And the white region is the one which is not explored, which is that one, which is still, I mean, you can count the orders of magnitude. There are still many of them. So there is a lot of research to cover the gap and to exclude the CSL model, who knows, or perhaps to see a signal of something that is beyond quantum mechanics. There was this experiment that, so you can see it in the archive, but as far as I know, that the data analysis was still under discussion, but I give it just that there is this paper from last year. And then, I mean, I just want to tell you that, just as to conclude, that we did research about and proposals for testing collapse models in space, where you have different environmental conditions. We used also not only translational jiggling, but also rotational things. It's a very interesting to work on theoretically. Then you can play with the mass distribution of the system to enhance the effect. You can play with cosmology. Now, this is now the story here becomes very long. There are more and more references. Okay, I couldn't put all of them. You can see the paper. So I just put our reference, but if you look inside, there are many references about cosmology. And we're also applying these things to quantum computing. Okay, so I don't want to talk about extensions about not white noises, to include dissipation. These are all sided tools that you can take. So I prefer to close here. So I thank you for the attention. I thank you, my group that does all the work, and the funding agencies. And again, thank you for listening to the talk.
Thank you very much, Angelo, for a very nice update. Thanks really for this exciting, better quantum story. The talk is now open for questions. Kindly use the raise hand feature, and I will try to unmute you. Yeah, okay, so there's a, okay, so what should I, yes. Bernd, please go ahead, unmute yourself and ask your question.
So I'm unmuted now, thank you very much, Tejinder.
Yes.
If I see your slides, I would guess that experiments seem to show more and more that the collapse models are not viable. At what point would you say they will be excluded. So how much time will be left for these models to be tested before we can conclude that?
No, so so there are two things in your question. So certainly this plot gives the impression that collapse models are less and less viable. I wouldn't say so, because I think that 80%, let's say, of this colored region, you would expect from the very beginning that it would have been excluded.
Ah, okay.
So in that sense, and these are the preliminary models. These are so on that I wouldn't say that they are almost excluded or they're clearly less and less. Of course, they are technically less and less viable, because if you restrict the region, then you exclude something. But I wouldn't be worried about that. At what point would it be excluded? Of course, there is no mathematical answer to that, but there is a criterion of reasonableness, which agree. So you are playing with these models. You know that you have some levels that you can touch to become more compatible with experimental evidence. But at some point, I don't know when, at some point you say, okay, that's the end of the story. You give up. The experiments do not confirm that. Now, the interesting question is with dark matter, have we reached that level?
Ah, I see. Yeah, that's one. Then I have a more theoretical question.
No, so there is no I cannot say more than that. But I want to make a point. There is a point. So let's say that mathematically speaking, you can always save a model, mathematically speaking.
By treating the parameter, yeah, of course.
You have to be reasonable. At some point, you have to give up. I don't know when that point will come, but it could come. There is
one question, Angelo. These bounds are always assuming white noise?
Yes. So I skipped. So, it was the last one. So you see that this. So sorry if I am going back and forth. This is for white noise. So if you release the white noise assumption, which is very reasonable, there you see that the bounds are retracting towards north, because a white noise is a very strong noise, so it makes very strong predictions, so it's easy to rule out. If you take a non-white noise, but not a crazy non-white noise, it's reasonable not white noise, then the effect is milder, and then the exclusion plot becomes smaller. The excluded region becomes smaller, as you can see from this picture.
Okay.
So again, this is a reasonable way to change the model.
Yes, I agree. Thank you very much. And some of these non-white models include dissipation, which I think it's reasonable, because one of the reasons why people use collapse models is to also better link quantum theory with thermodynamics.
Yes.
So to have intrinsic entropy production also on the microscopic level already. And this, even from a theoretical point of view, this might be more promising to look at an extension of quantum theory, which include dissipation on a fundamental level.
I fully agree with you. It's just that I didn't work on that because I was triggered by other things, but I fully agree on that.
Okay, thank you very much. I'm done with my questions then.
Thank you. More questions, please. Well, also, Angelo, I think any theory, underlying theory, which tries to derive collapse from more basic principles like trace dynamics, should in principle also predict the noise spectrum, isn't it?
Yes, I agree on that. It would predict. It would predict. I mean, it could be that. So if you push it further with the analogy with statistical mechanics, the first prediction would be a white noise again, because that's the simplest way of coarse grain, let's say. But a more detailed analysis would predict that. Yes, I fully agree. The point is that I don't know what the outcome would be, of course, because it's the underlying theory has not been developed.
I've been trying, but this is a difficult exercise. Predicting that collapse occurs is easier than coming up with additional information about what is the spectrum of the noise.
Yes, you're right. I agree.
Could you update us on this Kim result from 2022? What is going on there?
So this you mean
the Xenon data, which was this one. Yes.
Yeah. So basically, this is the same thing that we did. I mean, conceptually, of course, I don't want to take credit away from him. So the same kind of analysis that we did with the germanium detector. So data, spontaneous photon emission and then data analysis, but with a different dark matter, but related to a different dark matter experiment, the xenon, data experiment. So the paper, so my knowledge is a bit old by now, but the paper was in the archive, and the claim was that this extra purple region has been excluded, in particular the GRW value, which is psychologically important, so to say, has been excluded. But then I've heard that there was some discussion between the author, Kim, and the Xenon collaboration about the data analysis, which I have no idea which kind of discussion there was. And as far as I know, the paper has not been peer reviewed and published. But again, things might have changed in the last couple of months. I haven't checked actually.
Okay.
And I don't know, when I ask experimentalists, they don't give me a clear explanation of what's going on. I haven't insisted actually.
Okay. Yeah. Kinjal is here. Kinjal, go ahead, please. I have to unmute you.
Oh, nice to talk to you, Kinjal, after a long time.
Nice to see you after a long time. So, very nice talk. So I just wanted to learn about two things. One is that here when we talk about a collapse and the classical or a macroscopical states, those are apparently different from the classical states being discussed in the entanglement literature typically. In the literature of quantum entanglement.
Say it again, I didn't follow you.
For example, when in quantum entanglement literature, the states which are dubbed classical states, they still possess position superposition kind of thing.
Yes. So you mean that because it's not a Dirac delta, you mean?
This is not a Dirac delta. So therefore,
yes,
are still subject to these kind of CSL fluctuations.
Yes.
The dynamics will still, I think there is a comment that someone cannot hear me properly. So let me try to speak loud. So what I'm trying to say that if there is a study from the point of view of entanglement decay due to CSL dynamics.
I mean, no, no, it's doable, but I don't think that anyone did it.
And is there any, meaning, is this experimentally feasible? Because typically what I hear that entanglement tests are also one of the very precise tests going around. So
no, I suspect so. I don't know because I'm not an expert in this field because it's basically quantum information. But my bet is that these entanglement tests have been done either with photons or with single atoms. And in both cases, the collapse effect is basically negligible. So I'm sure that the experiments have been done very well, but that I'm ready to bet that they are not sensitive to collapse effects.
So for photons, for example, but I hear that entanglement up to 1 million photons has been achieved.
Yes, but million is nothing. Million photons is nothing for collapse models.
Okay.
Because the equivalent, the mass equivalent. The point is that you should consider the mass equivalent of a photon. So given the mass equivalent, so I don't even think that 1 million photons make up an electron probably in terms of equivalent mass.
Okay.
I don't know. I would like to make the numbers, but I don't think the 1 million photons make an electron in that sense.
Okay. So yeah, mass equivalent would be nothing compared to this.
Yes. Because I mean, if you want, because so typical. Sorry if because generally no one only did something on collapsing photons. You can do that, but then I mean the most reasonable way of doing that is to take the mass proportional model. So you have to find a mass equivalent, which you can easily find of a photon, and then you find out that it's basically zero. It is the mass, and so the collapse is also almost zero, which justifies why photons can live in a quantum state forever, basically. Also according to collapse model. So the point is not number is not sufficient. 1 million is a big number, but it's not sufficient.
Right.
1 million of what?
Yes. So my second question was also slightly tilted towards that. Since you're saying number is not a good quantity to just quantify completely, and energy equivalence is more reliable number, or mass equivalence is a more reliable number. But if we try to go from quantum mechanics to quantum relativistic quantum mechanics or quantum field theory, then we learned that even energy equivalence is observer dependent kind of thing. So some observers may find a different energy scale corresponding to given energy scale in one frame. Whether this should remain a viable parameter in the relativistic regime, a number or energy equivalence, or something more covariant should come about.
Well, that is not the answer is not trivial, because that goes into the that goes into the issue of how to make a relativistic collapse model. So so basically I do not have the answer, because I mean I would tell you that of course you don't take the energy, you take the stress energy tensor. You take somehow you collapse you couple the collapse to the field to the stress energy tensor. Then you would have a covariant way of doing that. But I have no idea how to turn that into a model.
Right. Yeah. So typically the most phenomenological quantum field theory models, they also look for number expectancy or squeezing or something. For example, in inflationary dynamics, when we also studied, some squeezing or number occupancy, those kind of things are typically taken as a parameter of causing collapse. However, they are not fully relativistic in that sense.
Say it again, sorry.
So some of the literature I am familiar with of quantum collapse models in inflationary context where they apply on quantum, there the parameter to distinguish strong collapse versus weak collapse is either squeezing of a state, which roughly relates to number occupancy on a particular given mode K.
Okay.
That is not a covariant quantity, that changes from frame to frame.
Yes. Yes.
So therefore that is not fully relativistic in some sense.
I fully agree. In fact, the way I would know to do collapsing cosmology, which is the way we did it actually, is basically to pick a reference frame, which is the cosmic one, and to do the collapse there. So it's not relativistic about it. But I mean, but if you push me, I do not think that you can make a relativistic collapse models. And if you push me even further, I wouldn't say that that non-locality basically calls for giving up a special relativity in a way.
Yeah. So Angelo, I'm tempted to make a remark on that. And my take on relativistic collapse models is that, yes, I agree. Firstly, special relativity would have to go in some sense, but one can still make a relativistic collapse model provided I accept to raise time also to the status of an operator and allow for spontaneous collapse in time, which goes beyond, goes beyond collapse models. And there are some very interesting ideas. I think we talked quantum interference in time. So in principle, we should test for spontaneous collapse in time the way you are testing in position space.
No, I agree with you. So I was speaking about the standard frame of collapse models, not about this extended way of doing that. Yes, I agree.
Yeah, thank you. Thank you. Bernd, please go ahead, and then soon we should be. You're okay to take one or two more questions?
Sure.
Yeah, please, Bernd, go ahead. Yeah, sorry, I keep forgetting to unmute. Yeah, please.
Oh, I had trouble with unmuting myself. I have a question also related to relativistic invariance or not. So you start with the Schrödinger equation, so which is also non-relativistic. Has anybody attempted to start with relativistic quantum field theory and generalized relativistic quantum field theory to allow for some kind of collapse? Or are you aware of papers describing the limitations of measurements you would get if you include relativistic effects? It's already started in the 1930s with a very famous paper by Landau and Perls, where they looked at what including relativistic effects into the measurement scheme of traditional quantum theory would entail. Then there was a famous refutation written by Bohr, but Bohr's refutation relies on using macroscopic and classical measurement devices. So,
okay, yes. So the first part of the question, in a way, it's easy. So you take this dynamics, but for H, you put the Hamiltonian of quantum field theory. So in a sense, so one possible answer to your question, yes, you can do that with collapse models. So you just take a relativistic system. H is the Hamiltonian of the Dirac Hamiltonian, for example, quantum field theory. So you have a relativistic system that collapses.
Okay.
Probably the question was, but can you make the collapse relativistic? So the Hamiltonian is relativistic, but this collapse wouldn't be covariant. Of course not. It would not be covariant because there is a noise. It's sorry. No, wait, I'm going the wrong way. Because the noise, the noise is white in time, but correlated in space. So So to make the model covariant, basically the field should have a covariant correlation function. So what does it mean? That if you make it white in time, then you have to make it white in space. And then the model is physically excluded, because a white noise in space means that you are destroying any possible superposition, even the small ones. So the model is falsified by experimental evidence. If then you go the other way, it's not white in space, then it's not white in time. If it's not white in time, it becomes a non-Markovian model, and then the Tomonaga-Schwinger equation basically becomes not integrable, and then again you don't have a relativistic theory.
Okay.
You cannot know, you know how to move it. So that is the problem. So what is the source? So,
go ahead.
So this is, if you wish, a kind of mathematical answer. What is the true answer to that? Non-locality. So you can make, so the point is that you can make a collapse model, mathematically speaking, which is local and then relativistic, fully relativistic. The point is that it would be falsified by experimental evidence on Bell tests. You want to recover correlations. If I have an entangled pair and I measure this, I find that. So if you want to have also this feature, the collapse has to be non-local. And then non-locality means no relativity. So asking for relativistic non-local collapse model is just like trying to put a square in a circle.
I see, it's not possible because of the Bell
inequality. For me, it's not possible. Now, if you talk with Tumulcian,
that problem already exists even in relativistic quantum field theory, because it treats time and space differently, all said and done. Like Stuckelberg in his formalism tries to do it in a fully covariant way. I think first we have to sort that issue before we come to collapse. What is a fully relativistically covariant quantum field theory?
Yeah. I agree. Of course, you have. This is the first part of the homework we have to do before we can go on and discuss what I had in mind. You are absolutely right, and I agree.
Thank you. Okay, great. So I think people also dwindling. Maybe we could wind it here, Angelo, and wish you a happy family time. And thanks for coming.
Very much.
Oh,
thank you again for the invitation. It was a pleasure.
Okay, great. Okay.
Thank you very much, Angelo. If I can just quickly come back in, and that was utterly fascinating. Very good discussion. Do people want to stay online just to continue the discussion a little, or shall we just call the whole meeting to end at this point?
We can stay for a little bit. We can, Angelo can proceed, and the rest of us will wind up slowly, just in case there's some more discussion.
Okay.
Right. In which case, once again, thank you very much indeed, Angelo. Thank you.
Thank you very much to you for organizing the series and this invitation. And okay, see you soon. Bye-bye. Have a nice evening. Bye-bye.
And thank you very much.
Yeah, if there are any questions on general discussion on collapse models, we can still talk, otherwise we can wind up. I think Angelo had to leave because he has family constraints, so we didn't want to keep him longer.
Holiday season, so to speak.
No, I think it's the second baby.
Oh, okay.
I was going to say the exact opposite of a holiday, actually. Just the opposite.
It is very much of a family constraint.
Yes, very much so, yeah.
The baby was born.
But anyway, yeah, so get back to what we, yes.
Okay, so Tejinder, I would like more to discuss on the lack of full covariance and quantum field theories we already have. So, of course, this is an important and crucial point before we can go on.
Please go ahead. You were saying something?
I know it was a question. So can you?
Yeah. Actually, so if you know, Stuckelberg just after the Second World War, around Feynman's time, in
the 1940s, yeah.
Right. He has his full. So what I understand from how Lawrence Horowitz extended his work. So he has a book called Relativistic Quantum Mechanics, in which right from the beginning, time is also an operator. You probably know this already. So, an auxiliary time parameter is introduced to play the role of time.
And an evolution parameter, I think that's how he framed it. It's called explicitly an evolution parameter because it's not directly related to what we call coordinate time.
Right, it's different. The coordinate time has become an operator, and the evolution time, which I am tempted to identify with what I've been calling Cohn's time in my work. So that comes with the non-commutative geometry. And in the space-time manifold, space as well as time variables are both allowed to become operators. And then this is a theory more general than what we normally call relativistic quantum field theory. It includes that as a special case. And the very interesting point is that now, because coordinate time has become an operator, you have this possibility of quantum interference in time. It's like being in one place, but at two different coordinate times. The wave function can be at two different coordinate times and interfere in time. And some people are talking about this. I wish experimentalists paid more attention to this. In principle, at least a doable experiment, which would be very rewarding if, so this leads to fringes in energy. Instead of fringes in position space, there are fringes in. So it's like the head of the wave function meets the tail before the head has left the slit, kind of thing.
Okay, so you have a kind of temporal non-locality there.
Yes, temporal non-locality, absolutely. And then if you could pass it through two time slits at the same position, then you see energy fringes. And some attempt is being made. I don't have expertise on this. Some talk is there. So this, I think, would be a very interesting experiment. And this comes with also extension of the collapse models to collapse in time, spontaneous collapse of time superpositions. And so the picture is that standard quantum field theory works because spontaneous collapse in time happens very rapidly. For all purposes, time is classical. It's easier to see position superposition and interference than it is to see time superpositions and interference. So,
and I think in a sense this would make the measurement problem of linear quantum theory even worse, because you would have a process to unfreeze time. Otherwise, time would just be a non-local entity, and you would have not the kind of time we experience, though, which can be subdivided and which, in a sense, sorry, relativists, they will also say this is nonsense, but which either flows or which you can give as this infinitely extended line, which you use in relativistic theories or in general relativity until the singularity at the beginning of the Big Bang. But this would all be lost. You would have some kind of, I think Weizsäcker worked on this. He called it extended present. So
we have Cohn's time as a parameter, which is like Stuckelberg's evolution parameter. So the whole space-time manifold is evolving in Cohn's time. So we have this curious situation in our physics world today that we have seen classical phenomena in space and quantum phenomena in space, but we have only seen classical phenomena in time.
Yeah, that's true. So time is somehow singled out as the only true classical variable so far.
Yes, but in principle, that too is quantum. Coordinate time is also quantum. That's the claim.
Okay, then I would look forward to seeing how this experiment. Let's say
Can I just come in and so sorry, I didn't.
Yeah, please go ahead.
Michael, go ahead.
Michael?
Yes, hello. Sorry, I accidentally muted myself again. I just want to say this that you've just outlined, this work of Stuckelberg, which, and particularly the connection with the suggestion of Kohn, it seems remarkably reminiscent to me of some suggestion which our friend and colleague, who of course spoke second in this series, Basil Hiley, did a few years ago with Harold Atmanstracker. They had a paper on the notion of what I think they're called moments, which were precisely these kind of non-local extended, a kind of quantized time coordinate, which allowed for superposition of times. Although, of course, in practice, sorry, I'm trying to remember exactly some of the details of the proposal, because it's several years since I looked at their paper. I think it was published in about 2017, and you can extract the kind of classical time parameter in a limited kind of weak field limit. But the suggestion of this linear superposition of times, it does seem to be remarkably reminiscent of what you're telling me about Zuckerberg. And they did also specifically, sorry, just to finish super quickly, they did specifically link their proposal to the suggestion of Kohn.
Ah, they did?
Yes,
Huh?
yes.
I
Can
should look it up. It is a pity that more experimentalists are not looking into this quantum interference in time.
Yeah.
It would be a major advance.
Particularly since it doesn't seem to be, that difficult conceptually to envisage experiments that might, one can imagine the phenomenology which would be detectable within.
I agree. Considering the kind of time intervals we are now able to measure,
Yes,
I think if effort is invested, this might be a doable experiment.
let's just suppose this experiment is done and it shows that time is classical, so you don't have any interference in time. What would this mean if they really would prove that time needs to be a classical variable? And I think this is also important for relativistic causality, because if you want to construct light cones, you need to assume that you have infinitely precise moments or points in time. And a time operator, if it doesn't commute with another operator, would mean that time becomes fuzzy and that you cannot use sharp light cones to define causality.
Yeah, my take on that, Bernd, is that if we look at the space-time manifold, the thing that we call time there is not the time of evolution. It's not the time that flows. It is coordinate time, or what?
Not evolution time, so to distinguish between.
I would call this, I think, call it common time versus absolute time or something like that. So I think there's a conflation of ideas when we call coordinate time time. We should call it something else, so that once and perhaps I thought Einstein oversimplified when, in going to special relativity, he gave up Newton's absolute time. Newton was clear that absolute time and common time are different things, but they are identified for the sake of measurement. The only way to measure absolute time is to identify it with the common time, the coordinate time that clocks measure. He was very clear about that. And in making coordinate time covariant and relativistic, I don't understand why Einstein had to give up absolute time.
Because Einstein was, when he developed the two theories of relativity, he was very operational in his mindset. So he considered, how do we measure things? What is a physical clock? But of course, he didn't, I mean, he was very much inspired by Ernst Mach, who said space and time don't exist in itself. They're just a way to organize events and the relations between particles or matter. And originally, Einstein wanted to implement Mach's principle, and he hoped that the entire space-time manifold could be derived from its material content, which did not work in general relativity. Otherwise, we wouldn't have, for example, gravitational waves or the de Sitter solution. But this was his reason. He thought time is basically, he said time is that what we measure with clocks. And if we cannot measure something like absolute time, it doesn't have any operational or physical meaning. It would be a metaphysical background construct where we don't have any experimental access to. And this was basically the reasons why.
I think this leads to a problem in quantum theory, isn't it? Because in quantum theory, if everything is quantum, all material systems are quantum, we cannot anymore talk of clocks, classical clocks.
Classical clocks, yes, because how do we measure a classical time? We would need classical matter then, yeah.
Right. So for that reason, I felt if Einstein had retained that absolute time, it would come very handy in quantum theory. The way Stuckelberg had to introduce an evolution time. And perhaps from Cohn's point of view, this extrinsic time, which is over and above the time coordinate of Riemannian geometry, is very useful, I think. And that is the true evolution time, to my understanding, what Cohn's.
And then we could use this evolution time to define dynamics and see what is causal and what's not causal, and we would not fall into the trap that we cannot make coordinate time fuzzy because, okay. So basically, this looking for interference in time experiments are a win-win situation. Either we prove that everything is quantum, also time, or we prove that something like absolute time does exist after all. So for an experimentalist, you cannot do anything wrong. You can only win by performing the experiment if you do the experiment correctly.
It's a win-win experiment. Either way, the result will be very important.
Any result will be a huge step forward in our understanding of time and how to reconcile. Yeah, so basically it's a win-win. So you cannot lose with this experiment.
Which, if I may come in very quickly, makes it all the more strange that nobody seems to be looking at. None of the experimenters
this is really strange.
Even looking at this suggestion. It makes it all the more striking. Since yes, and can I just make a very brief historical observation, which of course you're absolutely right in what you said about Einstein's at the time, certainly that of the construction of the special theory. He was very much had kind of bought into the generally kind of operationalist stance about concept formation in physics and was broadly in agreement with Marx's viewpoint. But he did move, I mean, very large down to the influence of the fact that approach clearly failed in general relativity. He had moved a long way away from that already by 1920, and in all his later writings, his exploratory writings in GR, he has a much more let's say broadly kind of rationalist, top-down, a prioristic viewpoint about concept formation, and stresses the crucial conceptual role of mathematics in concept formation rather than, I mean, at the expense of the earlier stress on operationalist validation of concepts. It's not that he rejects obviously empirical constraints on the theory, but or that he's a kind of any kind of a priorist, but he does move very definitely in the direction of a much more kind of top-down structuralist view of concept formation.
True. I mean, after finishing general relativity, I mean, if you look at all of the alternative theories of gravity to compare to general relativity, if you look close into the history of the field, because people always say we prove Einstein right if we confirm general relativity, you prove Einstein until 1916 right, you prove Einstein after 1916 wrong, because not all, but most of the ideas how to generalize general relativity came from Einstein, actually.
Exactly.
So he worked on
yes,
like line theory, on torsions.
Yes, indeed. No, that's a very worthwhile point to make. I agree.
So I think people are more in love with general relativity than Einstein ever was. So Einstein.
Well, of course, it is. In fairness, it has become even clearer than it was perhaps to Einstein himself, just how internally, I mean, deeply, beautifully, sort of structurally tightly knit the concepts at the basis of general relativity are. I mean, the inner unity of the theory, and the fact that it's really almost impossible to change even the tiniest piece of the theory without ruining the whole structure, has become even more manifest since Einstein. So I think the reason that people are so in love with it, and given that it is such a beautiful theory, is not sociologically that surprising. But I agree with the remark that I think you make a very valid point.
Can I use this time, Michael, to ask you to share some highlights of the MON meeting? I'm very curious.
I hate to say it, Tajend. I wish I could say yes, but the problem is I'm afraid I have to go myself at the moment because I've got to move a whole lot of books out of the coach house in the next 10 minutes before we close. I do apologize, but I tell you what, next time, which is only going to be next Friday, I will definitely make the time to give a short report on the MON meeting, and also that will give me the time to refresh my memory by listening to some of the talks. It was indeed a very interesting meeting. I'd like to talk a little bit about that, but if you could give me a breathing space for about to do that next week, I'd be very grateful.
Great. So maybe we can wind up now. So thanks,
Yeah.
everyone.
Thank you very much.
Okay. So I'll say bye. Bye,
And I'll say
Michael.
bye-bye and thank you again to us, to Angelo and to Sudhinder and to Brent and to all of the speakers and questioners and indeed everybody who's been here. Thank you again.
Goodbye.
We'll see you here again next Friday.
Ah,
See you
yeah,
next
for the-
week at Ashutosh Kotwal's lecture, July 21.
Okay,
Yeah,
fine,
which is a
we'll-
week today. Yeah, exactly.
Okay, thank you.
Okay,
Goodbye.
all the very best.